Got it. And we are, where was I here? All right, so what I've done is I've typed in 2 vectors. Can you guys see this okay, or do I need to make it bigger? Would it help if it's that big? Is that better? Okay, so I'll have to do some resizing if I ever forget to. So when I run the codes, I have to downsize it a little bit, then upsize. So if I forget, just say, could you make it bigger or smaller? Just be interactive. Okay, so I've got 2 vectors described, and I could say A plus B in quotes, and then here I could actually type A plus B and put that in parentheses. And let's see what happens. I like to have some space here just so I could see a little bit better. Let's see what happens when we run this code. Whoops, I hit the download button. So notice it adds the vectors for you, right? And that's one of the powerful things about this. We don't have to sit there and do the AX plus BX separately ourselves, right? If I want, I could write magnitude of A plus B, and then all I'd have to do is write mag here, and it's going to take the magnitude for me. When I run this, okay, it doesn't look very pretty, so let's do this. Let's put a space in there just so it cleans up a little bit. Notice it does these crazy amount of sig figs. For right now, the sig figs is something we can learn later in the coding process. There's a thing called an F statement. I think I've got something in the Canvas quiz that tells you how to do that. If not, let's worry about F statements and sig figs at a later time. So for right now, I'll ignore the fact that that's way too many sig figs to display. But it's working. Look at this. If I want a hat vector, I could do this, and there's kind of a lot of space. How about I just shorten this so it fits on the page? I could have a unit vector in the direction of A plus B. I just use the hat symbol. When I run that, there we go. It's a hat vector. All right. How's everybody feeling with just your basic vector addition, magnitude, and hat? Those are some of the most common things that we use. All right. And now I want you to think about this equation. Oops. X, center of mass, is equal to the sum of x sub I, m sub I, all over the sum of m sub I. All right. So now the question becomes, how can we do this? How can we efficiently add these all up? Obviously, I could do them one at a time, but that's not the point of this coding, right? We want to be able to whip this thing together. So I want to teach you about loops. So let's start with your basic while loop. While, let's define a constant. Let's say I equals 0. That's a constant, all right? And notice it's a vector or a scalar. What do you think? Scalar, it's just a number. It's not a set of 3, all right? And let's say while I is less than 5, colon. While I is less than 5. Okay, this is called a while statement. Line 4 of the code is a while statement. The while statement does this procedure. It checks a condition. The condition we are checking of is I less than 5? Well, look at line 3. Is I less than 5? Yes. We're going to enter the loop. The condition is true. We will execute the operations after the colon. Now be careful. In Python, the way you tell whether something is inside or outside of a loop is the indentation. Watch what happens when I hit return. Notice it's indented 1 level. Okay, so what I'm going to do now is print I. Now, if I just do this, what's going to happen? It's important that you learn this basic skill I'm about to show you right now. Okay, the idea is you have to think about the code and what it's going to do. First, I get to this, and that just says, okay, I've initialized a value to 0. Now I'm going to check this value. It's less than 5. That means I'm going to execute what's inside the loop. This means I'm going to print the number 0. Once I'm done with that, I'm going to go up and check this again. Well, I is still less than 5. It's going to print 0 again, and then again, and again, and again, forever. That's not a very useful code. So let's see if we could do this step. Whoops. Watch this extra step. I could say I is going to be updated, the old value of I plus 1. So now what is this code going to do? I'm going to start at 0, check the condition, it's true. I'm going to print 0, and then I'm going to add 1. Now, normally this would be something you would not write down on paper and pencil if you were doing algebra, right? It looks kind of weird. What we're doing is we're saying the new value of I is equal to the old value of I. So this is called an update type equation, where you're incrementing or changing the old value by some parameter. Now I'm going to clear this out. Here we go. Let's run this and think what should happen before we do it. We start at 0, we print 0, we change it to 1. 1 is less than 5, I'm going to print 1. Then I go to 2, etc. When is this going to stop? What is the last number we should see printed on the screen? Let's find out. There we go. So remember, after we get to 4, what happens? At some point, after you print the number 4, you add 1, that's 5, the while loop is no longer true. Now watch this. I'm going to enter and then shift tab. And I'm going to do a new print statement. That was bad ass. All right. How about bad ass, like a bad Egyptian snake? There we go. All right. So when I do this, the only thing I'm trying to emphasize here is, look, when we do these while loops, we're going to start with the number 0, and then we're going to do this code over and over and over again. And then when it's no longer true, we go to the unindented crap. So this is after the while loop. It should print this only one time. So let's clear that out and run it. That was bad ass. Okay, cool. Did that make any sense here, what the indent means? Is this a good pace, or am I too slow? Okay, I'd rather go a little bit slow because I know some people don't know anything. So again, if this is way too slow for you, you don't have to watch, just do it, do whatever you want. All right. Now that's a while loop. Oh wait, let me show you two cool things. Number one, I'm going to hit Control Z. That's my undo button, right? So if you do something and you want to undo it, like let's say, oh, whoops, I don't want to delete that, Control Z. You may want to scribble that down on a piece of paper or maybe just memorize it. Control Z is undo. Maybe you already know that. Here is something else that you might not be familiar with, a comment. So in Python, the pound symbol or the hashtag symbol is a comment. What this does, notice it changes color there. Here it's all pretty, and then it turns to this kind of light gray. What this means is the computer will not try to read this line and make sense of it. This can be somewhat useful if you're trying to make a note to yourself like, this code is so amazing. If I wanted to say that, but not have it screw up the computer code, I could do that. So that's a comment, okay? Now, the reason I'm mentioning this is sometimes you can use a comment to trouble check your code, debug it. What you can do is you can write code and then comment things in and out. I'm going to show you another trick. Watch this. Control / that's under the question mark. You can comment out large chunks of code in bulk. Do you see that? Okay. So control the / that's next to the shift. All right, that could be useful. Now, what I'm going to do is comment this out. And when I do that, none of this code will execute. So when I run this program, nothing happens at all. There's no program right now. So that's comments. Finally, one last trick. We're using the internet, right? Every once in a while, the internet will screw up on you and not save your stuff. So here's a trick you can do. If you've been typing for a while and then your code won't run for some reason, Control A, Control C. That means copy everything that's on the page, then you can refresh the page, and if all your work gets erased, you still have it cached in memory, and you can just paste it back in. Did that line make sense? So basically, if the computer's about to crash on you or doing something weird, just hit Control A, Control C. That's copying all your work and paste it somewhere. You could either hit refresh and paste it back in, or you could paste it into a Word document and then paste it back. At least you won't lose any work. Got it? Those are kind of the three main things: how to comment, how to undo, and how to survive a temporary crash on the internet or something. Okay, ready? Now here's another type of loop I'm going to show you called a for loop. Okay, and in particular, I'm going to use a special technique here for, how about we do it this way? I in a range, parenthesis, parenthesis, colon. Now I'm going to fill in some stuff. You're going to notice that sometimes I get in this habit of doing the opening paren and the closing paren at the same time, and then I go back in to do my work. That's just so that I don't forget a closing parenthesis. A closing parenthesis is kind of annoying to find. Now, in this case, I'm going to say, how about 0 to 1, 0 by ones with an upper limit of 5. Let me kind of explain this. I'm just going to put in some extra spaces here. You don't need that. You don't need that space. Oh, thanks, Jaden.
Sorry, yeah, you can ignore my chat.
No, that's great. That's awesome. That's perfect. Okay, so this is going to be the start value for I. For whatever you wrote right there. So you could call it I, you could call it cucumber, you could call it Gandhi too. Whatever you call it, this is the start value for that name of that parameter. Okay? So we're going to start I at 0. This is the increment size. It's how much you increment . And then finally, this term right here means less than 5. So it's very similar to what we wrote up here, but it's just a different way of writing it that's very compact. Notice something special in line 8. You don't have to tell the computer what I is before writing this line of code. Said another way, you don't have to initialize I to 0. Got it? So watch this. I've got questions about that statement. Does everybody understand what the numbers mean? The first is the starting value. The second number is how much we're going to increment each time. So like I plus 1 in this case. And the last number is the upper limit. Maybe I'll write upper limit. And to be clear, the upper limit uses a less than symbol, not a less than or equals. That's going to matter. Okay. Now I'm going to come into here and just say print I. Whoops. Like this. When I run this one, it should do the same crap. Oh, what did I forget?
I think your second number is your upper limit.
Oh, did I screw it up? Thank you. My bad. There it is. You got it. So I switched these. Ah, that stinks. Let's clear that out. Thanks for catching that. So, all right. Well, there we go. So this is start. upper, and your increment. Thanks. All right, so in this case, I hope you see the difference between lines 8 and 9 and lines 3 through 6. Lines 8 and 9, you have to kind of understand it a little better. You can see even I screwed it up, but it's a lot shorter to write. So you may end up discovering you like this lower limit. And notice again, there's the colon at the end and the indent. Whatever's indented is inside the for loop. Is everybody okay with your basics of for loops and while loops? Okay. So now let's see if we can put this together and put that center mass equation on it. Whoops. Clear all drawings, get rid of that. I'm going to do this. What I'm going to do now is click my name and I'm going to create a different new program. So something you may want to do is every once in a while, just start a new program, right? And you could name it, you could use folders. You can see I've got a bunch of different folders here. The idea is if you use a new program, you can basically at some point, if you get a lot of work done, you might want to save that work and not mess with it. So you create a new program and you could copy your old work in and then modify that work. That way, if you screw everything up, you've got something to back you up. Did that make any sense, what I was trying to say? Basically, every once in a while, create a new program. That way you don't keep changing one program all the time. Now, are there smarter ways to do this in the long run? Absolutely, but this gets us started quickly. That's why we're using GlowScript. So let's do COM uni rod together, okay? So let's make the center mass of a uniform rod. I use the period. You can use other symbols, but some of them don't take. I forget what takes and what doesn't. So I did COM of uni rod. All right. And maybe we could sketch something here. We're probably going to have a coordinate system, right? Okay, and then I want to have a rod here. Oops, let me do one other thing here. And we're going to have a rod. And the idea is I want to build up the rod out of point masses. So the idea is there's two styles. We could build it up just give me a second here. Sorry, I didn't use exactly the same number here. Trying my best to give you an idea here. I want you to notice something very subtle. All right. In particular, notice that the top model of the rod has spheres at the very end, whereas the bottom model of the rod, we could say, is the spheres are entirely inside. And it turns out this lower style will actually converge with a lower percent difference more rapidly. What? Basically, you could use less computer memory and get better answers most of the time if we choose this bottom style. So rather than trying to put a point mass at the very left end and the very right end and then space them equally in between, what I want to do is I want to put the left edge of a point mass right here and then put the next one next to it, et cetera, and go on. So my goal is to model this thing with the lower style. Did that make any sense at all or not? Basically, there's a slight computational benefit to doing the lower style. That's why I'm going to teach you that. Is that okay? Okay, so then in this case, let me do something really quick. I'm just going to put those inside there so you can kind of get a better feeling of what we're trying to do. My goal again is to build this thing and let's just say we want to take this rod and I want to approximate the rod as 5 point masses. Okay, that's going to be our goal. Now, what are some parameters that you think we might need? in this calculation. One of them is n, the number of point masses, right? We want to use 5 point masses, so I'm going to define that in my code. What are some other attributes if we were trying to get the center mass of a rod that might be useful in real life? Dimensions of the rod. So I'm not sure if we're going to need all this, but we might want to know the length of the rod. Maybe we need its total mass. So some attributes of the rod. And there's one last bit of information that might be useful here in this particular picture. How far it's spaced out. So I'm going to call that symbol A. That's the amount it is spread out from the amount it's shifted from the origin. Is everybody okay with that? So those are the constants I want to use in my code. I'm going to define them right away. I'm going to say n equals 5. I'm going to say a equals, I don't know, let's just say 3. And let's say L equals 5. Okay. That hopefully will make some of the math a little bit easier. So if we want to draw a coordinate system, maybe we should draw an x-axis and a y-axis really quick. What I'm going to do is I'm going to show you one particular way to draw this x-axis. All right, and I'm just going to do it with you live. That way you can understand it. Again, if you don't like this, watch the training videos. So here's an x-axis. Now, what I can do is I can modify properties of this x-axis. Are there other ways to do that? For sure. But I'm going to say the radius of this axis, it's going to be a cylinder. Let's say the radius is 0.2. All right. And I'm going to say the x-axis dot position. Position, is that a vector or a scalar? Is position a vector or a scalar in physics? It's a vector. This is actually going to be the left end of the coordinate axis, not the left end of the rod. So I'm just going to say negative, how about negative 10, comma 0, comma 0. Whoops. So the idea is the left end of the rod is going to be over there 10 units. To be clear, what am I telling you right now? This is going to be the left end of the coordinate axis right there, negative 10. All right. Finally, there's one more major attribute here. How about the x-axis dot axis? That tells you it's a vector pointing from the left face to the right face in this case. So by choosing this to be 20, that should make a rod with the left end that is at x equals negative 10, y equals 0, z equals 0. The length of the rod will be 20, so it should be centered on the screen. It should be 10 to the left of the origin, 10 to the right, and its radius should be 0.2. Because I have not specified a color, the default color is white. Now, what I'd like to do is run this before I get ahead of myself to make sure I'm not making any screw ups. So let's run this. Now, here's where I have to kind of shrink my screen. There it is. Wow, we've got an x-axis. All right. How's everybody doing? Is this still okay? All right. Now, what if you wanted to do a y-axis? What's the fastest way to do it? Cut and paste. Grab that. Control C. Control V. Change all the x's to y's. The radius, I'm going to leave that the same. What do I need to do to the y-axis dot position? If I want to do a y-axis, what should I do? Yeah, so in this case, let's do just -6, 0, and actually let's do -8 and 16. Basically, we'll make the y-axis a little bit smaller to match the aspect ratio of the computer screen. So at this point, hopefully that will get the y-axis. I'm going to run it. And then I have to scroll out to see it. There it is. So I've got my coordinates. Remember, when we do center mass, we always want to have a coordinate system for reference. All right. Everybody still good with your coordinates? Okay, here's where we get to something new. All right. So let me write this. I guess I'll do it on the screen here. Give me a second here. You know that X, center of mass, is an equation given by the sum of X sub I, M sub I, all divided by the sum of the mass. And the M sub i's are going to be the mass of each of these balls up here. So this is I equals 0, I equals 1, all the way up to I equals 4. Notice the top number is n minus 1 in this case. So when we're computer coding, usually your constants are going to start at 0. So we go from 0 to n minus 1 in this case. Now, what I want to do is I want to introduce a parameter here. Oops, let me make this just a little bigger. Can you guys see that okay? One more. There we go. All right, and now let me clear out some of this annotation crap. We're going to get rid of this. All right. Now the idea is I want to define some constants here or some blank materials. And what I'm going to do is I'm going to write numerator equals an empty list. Denominator, let's see. And let me see if that's how I wanted to do this one. Actually, let's just make this a vector. All right, let's do that. And let's make the denominator. Does the denominator need to be a vector or a scalar for the center of mass calculation? It's a scalar. So the numerator has to be a vector because it's got an x in it, right? Whoops. This could be positive or negative, right? It's some kind of vector corresponding to the x coordinate, all right? So that's why the numerator has to be a vector. So the denominator we could just set equal to 0. And now what I'm going to do is I'm going to use a for loop. For, let's just say I in a range. Well, how about this? Let's say for x in a range this time, because we're going to be changing the x coordinate. And then let's try and remember what we need to do. The first number is the starting value. We could just say 0. The last number I'm going to say is n, right? Actually, let's do this. Sorry, I'm changing my mind how I want to code this on the fly. Not always the best way to do this. What I want to do is I'm going to try and use the coordinates of this picture that I drew up in the right. So I'm going to try a different style here just for fun. I'm going to say the x value is going to start at a, and it's going to end up at a plus L. Can everybody follow that? The smallest value of x is going to be at the value a. The largest value is going to be L plus a. And our increment size is going to be dx, a small amount in the x direction. Here, we run into trouble. This is how I would like to code it, right? And let me scoot down a little bit if that helps, just so it's higher on the screen. I would like to use this because this makes sense physically. It's going to say, I want my x value to start at a, end at L plus a, What's the problem if I tried to execute something like this? dx is, we have not told the computer what dx is. We told it about a and L plus a up at the top. Let's go back up to the top. Notice how we didn't specify what dx is. So what do you think would be a good value for dx? In this case, how much do we want these balls to be spaced apart? If the rod is 5 units long, and I want to put 5 balls in there, right, I would need to use a spacing of 1. But the trick here is this: we do not want to write spacing equals 1. We want to write it as L divided by N. So in this case, the idea is you take the total length of the rod, divide by the total number of spheres you would like to use, and that should be the spacing between adjacent spheres. By doing it this way, it's really easy to go back and change the length of the rod and still have the code work. Does that make sense? And notice by coding this, if we change what A or L is at some point later, the code should still work. Is this making sense why we're doing it in this long, complicated way? It's trying to make it easier to change the code to do more useful work later. Is everybody still doing all right? All right, here's the main trick. So what we're going to do now is we're going to say ball, let's say my ball equals a sphere. All right, there we go. You can call it my sphere if you want, if that makes you happier. How about my DM? Ooh, how about that? How about just DM? No. I'm going to say my sphere. Sorry, vacillating on my decision here. All right, so now we need to put the sphere's position somewhere. My sphere's position is going to be a vector, and I need to specify the X, Y, and Z coordinates. Okay, we're going to keep this simple for right now. What do you notice about the Y and the Z coordinates of every single sphere in this particular picture that I have drawn on the screen? What's true about the Y and the Z coordinates? They're on the axis, so they're both going to be 0. Is everybody okay that we could just put in 0 for the X, for the Z and the Y coordinates? What do you think the X coordinate should be? Are all the X coordinates the same, or are they changing? Do all the spheres have the same X coordinate? No. So what we could do is we could type X. Now think about what this should do. Right? X is this parameter that's in our loop. What's the first value of X? A. Is that going to draw the sphere where I want it? No. Spheres are centered at their center. So I need to shift it over by how much? Dx would shift it over a full 1 unit. Do I want to shift it over a full 1 unit? And rather than say dx over 2, whoops, I'm right here. I would do it this way, plus 0.5 star dx. That way I don't have to read a fraction in the code. You know what I'm saying? Multiplication is easier to read than a fraction. So by doing that, that should shift these spheres. Okay. At this point, let's maybe throw in one more thing. Let's say my sphere dot color, and let's color them red to match. That should be a nice red color. 100. 100% red, 0% green, 0% blue. What do you think? Should we run it and see if it works? Let's run it. Okay, I'm going to run it. Now I've got a bunch of crap on here from Zoom, but there it is. It kind of looks like what we're hoping to get. You agree? Now, one of the things that might be nice, do you see how the balls are kind of overlapping each other a little bit? The default radius of these spheres is 1. Whoops. Man, I'm getting too much junk on here. Let me clear this out, clear this out, clear this out, clear that out. All right. I forgot to count the number of spheres to see if it was right, but let's make this a little bit easier. A trick that you can do is you could say my sphere dot radius equals 0.5 star dx. Now I could have just said the radius is 0.5, but the advantage of writing it this way is, again, if you change L or N, the sphere should be auto drawn to always not overlap. Now there might be pros and cons of this. We may want to hard code in the size as 0.5. That way they're always going to be the same size. There's pros and cons to that. I'm going to choose this way. When I run this, whoops, now I can see the spheres a little bit better sitting there on the axis. So I built this rod. So far, so good. All right. We're printing out the correct number of spheres. Did you notice that as well? And if we had tick marks, we could actually see where this thing is drawn. In fact, why don't we do that? I'm going to show you a cool trick. Somewhere up above, whoops, up above this loop, maybe right after the axes, I'm going to say rod underscore visual underscore guide equals a cylinder. Okay, this is going to just be something to show the rod as a visual. Now, in order to do this, I'm going to say rod underscore visual underscore guide. I know it's a really long variable name, but now I don't have to wonder what that is later. And notice I don't have to make a comment. I know what these things are. Okay, so let's just say that, whoops, let's change its dot radius to equal, how about 0.5 star dx. All right. And then I'm going to say rod, well, actually, I'll just yell this so I don't have to keep typing it. There's another trick we can do, opacity. And I'm going to change that to 0.1. So what that does is it makes it only 10% visible, 90% invisible. And that just makes it easier to see the spheres inside of it. Okay, but now I need to locate it at the correct spot. Anybody feeling brave? How would I place this rod visual guide in the correct spot? What properties do I still need to adjust to draw this cylinder correctly? Its position, and that's a vector, and the axis. So I need to change these two properties, and both of those are vectors. What is the position? Well, I could use the left end of the rod. What is the x coordinate of the left end of the rod in my picture? A. And now if I change A, it should still work. What is the y value and the z value for this picture? 0, 0. All right, so we got that done. What is the length vector in the x direction for the rod? How long is the cylinder in the x direction? L. And how long is it in the y or z? 0, 0. So what we're trying to do here, if you could, what we're trying to do is, you see this black outline that I have here? we're basically trying to draw that black outline on the screen so we can make sure we know what we're doing. All right. Let's run it. Oh, I could barely see it. Can you? I need to change the opacity and make it a little bit more opaque. So let's go change that opacity to say, what is it? How about, where did that go? How about, let's try 0.25, 25%. And there you can kind of see it now. Do you see it? Whoa. I can see that there's kind of a visual guide of the rod there. I can swivel it in 3D. It's looking like it's matching what we expected. We have 5 spheres drawn inside the rod. Is this pace still okay for you all? Is this working? I mean, this is a job skill, right? So I'd rather go slow and have you get it and have this lab be horrible and be 2 days long, but at least you get a job skill out of it than be completely worthless. So I'm trying to help you in your careers. I apologize if I'm not doing the best job of it, okay? All right. Man, this is a lot of stuff, isn't it? To draw something and make it look pretty. All right, let's go back. We have drawn these spheres. There's only 2 more pieces. We got to correctly change the numerator and the denominator. Well, in order to do that, each sphere needs a mass, doesn't it? So we've drawn these spheres. We've told it about the sphere's position, its color, its radius, but we haven't told it the mass of each of these spheres. How could I figure out the mass of each of these spheres? Well, I know the total mass is m, and the length of the rod is L. What's the mass of each one here? Oh, and the number that we're using is 5. Sorry. Which of those will help us get the mass of the sphere? M, L, A, N. Which two constants will help us get the mass of each sphere? M and N. So in this case, we could actually go up and define some more constants. In this case, we could say lambda. That's the mass per unit length, right? Oh, did I not specify the mass of this thing yet? Whoops. Let's specify a mass. Sorry about that. Let's say the mass is 1 kilogram. All right. So one of the things you could do with your comments is, if you wanted to, you could specify your units with a comment. So then it makes it more clear when we start to get all of these things. Notice dx would be in units of meters. So we can understand our constants. So now what I'm going to do is I'm going to define mass density lambda. So I'm writing a comment in the code to make it clear what I'm trying to do. We've got some constants now, the numbers here, and then the mass per unit length is mass over L for a uniform rod. Now, somebody else said, could I also use M over N? That would also work in this case. But I thought about it, and I'm trying to set you up for success in a non-uniform code as well. Can you see that okay? All right, so we've got our constants. What I want to do is I want to try and define this as lambda. Well, now I'm going to come down in here. I'm going to define dm, the mass of each little chunk. Isn't that what we call it in our calculus problems? So how did you get dm for a 1D rod in problem 9.33? It is lambda dx. Does our code know what lambda is? Yes. Does it know what dx is? Isn't that sweet? We're trying to make our code look as much as possible like a real physics problem because it's easier to understand and troubleshoot. What if it was a non-uniform problem? Whoops, lambda, what? Lambda. Later on, the only thing that's tricky in your final code will be figuring out how to change lambda to a function instead of a constant. But that's easy. We just have another line of code in the for loop where you do the calculation, say lambda equals some function for x. All right. So now we've got our initialized numerator and denominator. We're going to try and do the center mass calculation shown right here. I'm circling it a couple of times. We're going to try and do that center mass calculation. This is going to be the numerator for it. That's going to be the denominator for it. Okay. And what we need to do is each time we add a sphere, right, in this loop, we keep adding more and more spheres. We have to keep adding them into the calculation each time the loop does an iteration. So far, so good. That's our plan. We want to add the terms into the numerator and denominator as we draw them on the screen. Okay. So, well, numerator should equal the old value of the numerator, which is 0 as a vector, plus, help me out. I need the x coordinate of this sphere. How could I write that? That will get me the position of the sphere. Whoops, this is getting messy with all these annotations. Hold on. Get that lambda out of there. So the idea is, let me just write it for you and see if this makes sense. Whoops. Now I know this seems like a really long, complicated way to do it. You just have to trust me that this will pay dividends down the road. We're trying to do this the right way. And what we're doing is we're referencing attributes of the objects we drew, like its mass and its position. That is exactly what the numerator looks like in the center of mass equation. So the idea is each time you draw a new sphere, we take the old value of the numerator, add to it xi m sub I. Is that cool or what? Now, I would like to show you a cool shortcut. All right, check this out. We can actually make this section look a lot simpler if I just say plus equals. Instead of saying equals, now this is, you've got to get this right. And this, you're going to see this in a lot of codes. So the trick is, whenever you see a plus equals, it's very different than an equals. Plus equals says, take the old value and add to it. Well, that's exactly what we want to do in this case, right? We're taking the old value of the numerator and I'm adding to it x sub I, m sub I. All right. Did that make any sense at all? Okay. How do I update the denominator? What would I type to do the denominator, the sum in the denominator? What do you think I would do? The denominator is the sum of the masses. How could I add the mass of the current ball to the denominator? Plus equals my ball dot dn. Oh, wait. I made a mistake, didn't I? Up here, I called it my sphere. Down here, I called it my ball. Whatever. Let's change it both to my sphere. Do you agree? We got to be consistent. My sphere. Sorry about that. There we go. We've been coding for a long time. Do you agree? We should probably check and see if it still runs or if it gives us any errors. So let's do that. I'm going to run this. Then I got to change the zoom level. It looks like it's still running, but I don't see the center of mass written for me anywhere. It's doing the calculations, but it hasn't printed them out yet. That's basically all we got left. What do you think? You ready for this? Is it all right if I clear the left side of the screen with these annotations and pictures at this point? Is everybody okay with that? I'm going to clear out the annotations, all right? And then I'll make this a little bit bigger so you can see. So let's run through the code really quick. Just, I know you're tired and you want to be set loose, whatever. Let's learn here. Okay, follow me through the code. We define some constants that we're going to need. We specify the units. I figure out the mass density. I draw some coordinate axes. That's not very exciting. I draw a visual guide showing me the rod that I actually want to do. Fine. I initialize two constants that I'm going to use in the center of mass calculation. If I wanted to be even better, maybe I should have said COM numerator and COM denominator. The name doesn't matter, but since I changed it there, I better change it here. Now it makes more sense to me later. Instead of just some random numerator and random denominator, I know those are the center of mass. It's going to go through, it's going to draw them, it's going to figure out the mass of each one, and then it's going to add those terms to the sum. I'm done with the loop. I'm going to unindent and write COM equals the numerator divided by the denominator. Are there other ways to do this? Sure. But there's like, I don't know, I like splitting it into small chunks so that I can kind of try to understand each chunk separately. That's just me. Is the center of mass going to be a vector or a scalar? Okay. Why do you know it's a vector? Position is a vector, so we have somewhere in there is a vector in the numerator. Do you agree? So a vector times divided by a bunch of scalars, it's going to end up vector. So if I want to print the COM, I should put a statement on here. I'm going to use single quotes this time for fun. I'm going to print it and run it. Now I got to shrink this down a little bit. Oops. There it is. And look below the screen. Is that the correct location for the center of mass? What should it be? I got an idea. Let's do this. Don't we know A and L in this case? In theory, I'll call it COM_TH for theoretical. Shouldn't that equal? It's going to be a vector, right? So what's the x coordinate of it? It should be A plus, oops, what? Maybe if I draw it again, of course I erased it right there. Look, we have this thing here. We've got the rod. We know the length of this rod is L. I know this distance here is A. What should be the center of mass? What should be the x coordinate of the center of mass? A plus L over 2 in the x coordinate, 0, 0. So what I could do is try and compare these with the percent difference. But you can't do a percent difference on a vector. You can only do it on a component of a vector or the magnitude of the vector. So what I'll do is I'll say P diff equals I'm going to put in something minus something up top over something in the basement. Well, that should be the center of mass dot x. That'll be the x coordinate of the center of mass that the computer gave me. And then I got the center of mass theory dot x. And then I want to divide by the theoretical. And this should print it out. Oh, I need to hit a print statement. You can call these whatever you want. Am I going too fast or is this okay? I have no idea, right? I'm just trying to think it through what I would try and do if I was doing this one. And now when I run this one, I can scroll beneath it. Hey, you're not going to see that too often in a physics class. Percent difference is 0, right? Maybe it would be worth it to even do this. We could do this and print out both of them just so we have it on the screen, right? The idea is you want to make it easy to check your work. So I just did the same thing and printed out the theoretical value. There we go. So it just helps us see everything that's going on. I don't know. I feel like, all right. What do you think? Should I let you guys work now or do you have questions? How are you feeling? Thumbs up, like you think you're going to be able to do this. Thumbs down, it's going to be impossible. Thumbs sideways, you're not sure yet. Okay, everybody's all over the page. So we're here to help, and we want you to get this done. I would like to say one last thing before I set you free. So everybody should listen now, all right? Everybody should listen, whether you're a coder or not. Probably one of the hardest things is what happens if this is non-uniform. So I just want to explain briefly what happens. And one of your questions in your quiz is handle this non-uniform. Well, imagine if it's non-uniform. The density of the spheres would change as you go along. If the density of the spheres is changing, we can't do this outside of the loop. You can't define lambda outside of the loop unless it's a constant. Does everybody get that fact? If lambda is non-uniform, it's non-constant, you have to put it inside the loop. And what might that look like? Whoops, let me clear those annotations. You could go into the loop and maybe right here, you could define lambda equals some bad-ass function. And this would be a function that you type in. Be careful, right? It's going to be some function for x. Well, look, x is defined for the for loop right there. So you can use the value of x. However, you may want to actually do it like this and put it after the sphere. And this is what I recommend. Instead of using the x coordinate, I would use the ball's location, right? We want to use the x coordinate of the ball's position because we're not using the value x for the ball, right? Or the sphere or whatever. My sphere position. Let me write it. Got it? All right, let's go nuts. Figure this out. Whew. And if you get